Hi, welcome everyone. We're planning on going 30 to 45 minutes here and have a question and answer period at the end. But of course, you can type your question at any time. Um, I've been doing this for about 40 years, so I'll attempt to try to not get too much into the weeds. Energy Management, the company I work for, specializes in motors, drives, generators, and power quality. So today we're going to be talking primarily about the active methods of mitigating harmonics. But before that, I think we need to cover a little bit of background on harmonics. I'm not going to spend a great deal of time on this because we don't have a lot of time and we want to get right into the active filters. But we're going to talk about harmonics a little bit. I think you've had time to read the screen. This is a Fourier series, which is composed of fundamental sine wave plus a series of harmonic components, which are integer multiples of the fundamental. And that's Joseph Fourier, you can see when he lived. So what is an integer multiple? Well, what we're looking for is a sine wave. A sine wave doesn't have any harmonics. Or you could say it only has one harmonic, the fundamental, which is the first. But it has no other harmonic. It's the ideal wave, the one that we all want. Anything other than a sine wave has harmonics. And Fourier figured this out. Amazes me. I remember when I learned Fourier analysis in school, and it just was like opening a door and seeing a new world. So any wave shape, no matter what it is going to be composed of sine waves. And so a sine wave will only have the one sine wave, and in America that'll be at 60 hertz power frequency. And then anything other than a sine wave will have some harmonics, and those harmonics will be in integer multiples. So your second harmonic will be 2 times 60 hertz, your third harmonic 3 times 60 hertz, your fourth harmonic 4 times 60 hertz. And I've only gone down to harmonic number 9 because I wanted to keep the letters big. In theory, this goes to infinity. But in practice, it's those lower order harmonics that are of most concern to us. So there's the one we like. That's a nice little sine wave. This is not a sine wave. If you look at the dark blue, you see it kind of goes up. It has a little dip in the middle and comes down. Now, if somebody were to bring me in and say, hey, look at our current or look at our voltage, what do you think? I would say, ooh, that's not good. You have dirty power. You have corrupt power. You have harmonics. And so if they said, well, can you help me fix it? The answer is no. I mean, I don't know what to do with that wave shape. Fortunately for us engineers, along comes Fourier to the rescue, and we can put that into a simple Fourier analysis program, and we find out that that particular wave shape is made up of a 60 hertz sine wave, which we like, and a third harmonic. So you notice the yellowish color there has 3 cycles in the time that it would take to do 1 cycle on the fundamental, and therefore it's a third harmonic. And once I know that, then I say, oh, now I can fix it. All I need to do is build a third harmonic filter. If I take the third harmonic out, like magic, it goes back to a sine wave. Now notice that that third harmonic provides a dip in the middle. If we have a fifth harmonic, that provides a peak in the middle. So I'm just putting in 1 harmonic. Incidentally, the phase of the harmonic also makes a difference. So I can have a harmonic that is out of phase slightly with the fundamental, and it will produce a different wave shape. Now let's do this one. I call this classic harmonics. You'll see why. If we add 1/3 third harmonic, 1/5 fifth harmonic, 1/7 seventh harmonic, and so on, we get this wave shape. Basically, that's a square wave or a rectangular wave. And if I had continued to add more and more harmonics, that would just get smoother and smoother until it was a nice square wave. So this is something, if you're turning current on and then turning it off, then turning it on, then turning it off, you're gonna have a nice square wave, and those will be the harmonics. Now, so far, I have done this just with computer. Let's take a look at an actual waveform. So that this would be very simple, I used a single phase variable frequency drive. So it's got a single phase input, but it's got a 3-phase output. And as you know, a variable frequency drive can easily do that. I did this so that it would be very simple. And you can see if we have 80% third harmonic, 52% fifth harmonic, and so on, then we get this wave shape. Now notice that the bottom three harmonics, the third, the fifth, and the seventh, are the big ones. So if we can get rid of those, we can generally correct for most of the distortion in this wave shape. In this case, now the yellow is the sine wave current, but let's assume that it's voltage. You can see that the big problem with variable frequency drives is they have a capacitor on the DC bus. That capacitor is used as a power supply to drive the motor, and we wait until the voltage is very high, and then all of a sudden the diodes turn on and we get big pulses of current that charge that capacitor. So with virtually all variable frequency drives, that's the problem. We're charging that capacitor with pulses of current, and pulses, of course, are not sine waves, and they create harmonics on a power system. Now, for the engineers, this is the formula for calculating total harmonic distortion. The thing I want to point out here is up there in the numerator, that's basically the sum of all your harmonics. So you square all the harmonics, you add them together, and then you take the square root, and that gives you the harmonic content of that wave. And in the denominator, you have your fundamental current. So if you say we have a drive and it's got 100 amps and it's 30% harmonics, what I'd really like to do is say, well, 30% times 100 amps gives me 30 amps, that's my harmonic current. That's not the case, because I just divided my harmonics by my total current, not by the fundamental current. So if you want to be accurate about this, you have to go in and do some math, which for me says, forget the calculator, get on a spreadsheet, make it easy on yourself. And you have to separate out the fundamental component and the harmonics, and then you divide the two and you know what the actual harmonics are. Now, if I take that 100 amps and I multiply by 30% and I get 30 amps, that's still okay. It's not exactly accurate, but I'm in the ballpark. And so for the most part, if I'm not trying to get to very accurate numbers, that still kind of works. And I can still use 30 amps, and the 30 amps is conservative. So the actual harmonic distortion will be slightly less than that. How much less will depend upon the level of distortion. Now, harmonic voltage is exactly the same formula, you just use voltages. This is a harmonic voltage calculations on a standby generator. And the only thing I want to mention here is this X double prime sub D. So you know X double prime sub D is the subtransient reactance of the alternator on a generator. That is typically 12, 13, 14, 15% area. Whereas on a substation transformer or distribution transformer, you know that your reactance is going to be in the order of 5.75%, routinely. And so you could almost say this is almost 3 times as high as the impedance of a transformer. For that reason, you get much worse voltage harmonics. This is kind of Ohm's law. You multiply the harmonic currents times the impedance, you end up with harmonic voltages, and therefore the higher the impedance, the higher the harmonics. So you can get very low voltage distortion when you're on the utility transformer. Then you switch to a standby generator, and all of a sudden your voltage distortion goes way high. So we are trying to keep voltage distortion, as we'll mention later, down around 8%. You could have a utility situation in which you have 5% voltage distortion on the utility. You switch to the generator and you're more like 15%, or even more if the generator is smaller in size than the transformer. So moral of the story, if you have a standby generator, please do the calculations and make sure that your harmonic distortion is going to be under control when you're on the standby generator. Here's some typical harmonics, 6 pulse, 12 pulse, 18 pulse rectifier, and so on, your electronic computer, lighting, and so on. As you can see, the big culprits here are your electronics, your computers, and particularly variable frequency drives. Variable frequency drives are the #1 polluters of today's power systems. Now these are some of the effects of harmonics. Even though there's a lot here, I'm not going to spend a lot of time in this because I want to get more into the harmonic mitigation area. but you can see it can interfere with communication systems, give you high neutral ground voltages, cause misoperation of equipment, blowing of overload devices, lighting flicker, overheating of neutral conductors, all kinds of things. It can overheat your conductors, your transformers, and so on. Needless to say, harmonics means you have dirty power. Harmonics means you have high frequency noise. That's all harmonics are, is high frequency noise on your power distribution system, and that's going to not be a good thing for your power distribution system. This is my bad neighbor theory. I have a theory that there's two kinds of bad neighbors. The first kind of bad neighbor is the guy that plays Led Zeppelin at full blast at 2 a.m. when you're trying to sleep and you have to get up in the morning. But there is a second kind of bad neighbor. That's the guy who calls the cops on you when you're playing Led Zeppelin at 2 a.m. Now, I liken that to a power distribution system. You have drives particularly, but all kinds of other loads, UPSs, lighting, and so on. And when you, I just got a little message, sorry. So when you pollute that system, you can do one of two things. You can either clean up the harmonics, or you can have equipment on that system that's capable of withstanding those harmonics. So if you're having lots of problems, let's say with your communication system, well, maybe you can put a device on there that's going to filter those harmonics out just for the communications devices. But as we'll talk about later, we do have IEEE 519, which we'll address briefly. And in general, what we want to do is clean up the system rather than simply allow the system to become polluted and put on devices that are capable of existing in a high pollution, high harmonics atmosphere. Harmonics are pollution. They're like any other sort of pollution. You put a little bit of harmonics in, you get a little pollution. You put a lot of harmonics, you put a lot of pollution. So it's very common, and somebody may come out, want to sell you a variable frequency drive, and they'll say, look, you don't need to worry about harmonics because look how small this drive is in comparison to your system. And they're right. But what about the next drive and the next drive and the next drive after that? Eventually, you end up with a polluted system. In general, 100 1 horsepower drives is going to pollute about the same as one 100 horsepower drive. So generally, we're less concerned about the smaller loads and more concerned about the larger loads. And in some cases where they're very, very large loads, we have excellent harmonic solutions. On a 1 horsepower drive, harmonic solutions are not readily available sometimes and not really needed. But harmonics are indeed power pollution. Why does the utility care? Because there's no backflow preventer. On a plumbing system, you have a backflow preventer. It prevents dirty water on your side of the plumbing from getting back into the utility supply. Unfortunately, there is no such thing as an electrical backflow preventer. So maybe some of you smart guys can figure that out. If you could figure out a backflow preventer that prevented harmonics from flowing back into the utility, you might make a lot of money. So since there's no backflow preventer, the way we have to handle this is simply by doing measurements and by limiting the amount of pollution that you can put on the utility system. Now we're going to talk about harmonic techniques used with VFDs. We're not going to do a comprehensive view of these because of time. However, we will compare pretty much all of them as we get a little further in. We're going to talk just about the ones that are most popular to give you an idea, and we're going to focus more on the active mitigation techniques rather than other techniques. So here is a variable frequency drive. This is pretty much all variable frequency drives. You have 6 diodes. Whenever the voltage is higher on the line than this DC bus, then those diodes open and we charge the DC bus. And then you have IGBTs down here that turn on and off, generally creating a PWM waveform. Now look at the bottom, you can see that my THID, that's total harmonic current distortion, is on the order of 100%. That's horrible, and I think this is somewhat engineering malpractice to put out on drive with no harmonic correction. You could think of this as when you have 100 amps driving the motor, you're injecting another 100 amps of high frequency noise back into your power distribution system. Needless to say, that's not something we want to be doing. The most popular, cheapest, excellent way of controlling harmonics is with reactors. I happen to love reactors. My people at my company, I'm always saying, did we include a reactor with that? And they'll say, yes, yes, shut up. We can get AC line reactors and DC link reactors. They both do the same thing as far as harmonics goes, and all they're doing is adding impedance to the line. Reactors limit the rate of change of current, and because of that, they round the current waveforms, cause that capacitor on the DC bus to charge more slowly, and therefore we limit our harmonics. Down on the lower left, you can see this drops our total harmonic current distortion from 100% without reactors to in the range of 30%, we'll say, with reactors. Now, I want to mention a couple of things here. You can use DC link reactors or AC line reactors. The big advantage of DC link reactors is that they're cheaper. And so many drives come with DC link reactors as standard, and that's great. They already have some harmonic mitigation built into them. But the AC line reactors have two main advantages. Number one, they provide protection against surges. So all drives are subject to surges and spikes on the utility line, and AC line reactors will catch that because their limiting rate of rise of current, they tend to protect the drive, and so they will protect the drive from surges. They will also cause that drive to last longer. Most drives will have some MOVs, metal oxide varistors, that will have some surge protection, and putting on an AC line reactor does wonders in terms of protecting against surges. The DC link reactors, of course, are down in the DC link bus, and so not able to protect the entire drive. Now, you can have both, and if you have a drive that has DC link reactors, it's very simple to add the AC line reactors. You can see a picture of AC line reactors here. They're very easy, 3 lines in, 3 lines out. Very simple, very inexpensive, and they do a great job. Another thing that I want to mention, and I will bring up later here, many people don't realize this, but if you're using an active harmonic filter, which we haven't talked about, but will, you really need to have AC line reactors, because DC link reactors or no reactors tend to sabotage the effect of that active harmonic filter. And so we really highly, and I'm not saying the active harmonic filter doesn't work, it does. You just don't get as much correction as you would have liked out of it. And so if you're going to get it, you want it to really work well. We highly recommend when you have a active harmonic filter that you put AC line reactors on your variable frequency drives. Here's a picture of a cabinet that has a number of drives in there, and you can see this is your line reactor that is in front of that drive. This is the line reactor in front of that drive, so it gives you a little idea of the size. Now, let's go to 3-phase. With 3-phase, let's say that you're monitoring the A phase current. You're really going to get 2 spikes, one when A to B phase is high and one when A to C phase is high. So we typically refer to this as a camel's hump, and that is a typical wave shape for a 6-pulse standard variable frequency drive. This particular one has no reactors on. If we simply take this drive and add reactors, the waveform looks like that. So this waveform would be around 100% distortion. As you can see, we put on reactors. It's not great. We don't have a great sine wave, but it's 3 times better. You've eliminated 2/3 of the harmonic, and that's a much better waveform. So if you can't tell, I'm a big fan of reactors. Every drive can include reactors, and as I say, they're cheap. They protect against surges. It's just a really nice, easy, simple, reliable technology. This is a graph. It shows that all reactors are not created equal. The higher the impedance reactor, the better harmonics you get. And so some DC link capacitors will be down as low as 1%. So they are there for other reasons. They do give you some harmonic mitigation, but you might have like 50% harmonics. If you go to a 8% reactor, then you're going to be probably under 30% harmonics. Typically, standard reactor is 3%, and what we'd call a premium or a high impedance reactor is 5%. So those are the two that we tend to use on variable frequency drives the most. I want to talk about a hybrid filter. Hybrid filter uses 3 reactors and a capacitor, and a hybrid filter will get you down somewhere between 5 and 15% distortion, so much nicer. And if you want to know how this works, a little bit simplistic explanation, but pretty accurate, is that this reactor is tuned to this capacitor, excuse me, at about the 5th harmonic. The 5th harmonic is the worst harmonic on a 3-phase variable frequency drive. So we basically try to shunt the 5th harmonic. And then these are high impedance reactors that tend to just have their DIDT function, preventing rapid change of current. And this particular reactor here is quite a high impedance reactor. Excuse me. I want to mention 2 things. A lot of these, they will claim that you get 5% distortion. On a real system, we tend to see these run 7 or 8% distortion, and that's not bad. I mean, 7 or 8% distortion, I consider clean power, but very seldom will you actually get what's advertised. Now, this is a load reactor. I want to talk about that for a minute. If you go to most filter companies and you buy a passive harmonic filter or a hybrid filter, they all tend to have their own brand names for these, but when you get under the hood, they all tend to look similar. They don't come with 3 reactors, they come with 2 reactors. They come with this reactor, which we call the line reactor, and of the filter, and then they have a tuning reactor. They don't come with a load reactor, but if you look at the fine print, they will tell you that you have to have a load reactor. And if you say, well, why don't you supply one? They will tell you because some drives already have one. And that is exactly right. So if you've got a drive that already has, excuse me, already has a reactor, then you're good to go. If not, you need to realize you can't just buy this filter. You need to also buy a load reactor because you need all 3 reactors in order to get your maximum harmonic mitigation out of a filter at this time. Who developed the first hybrid filter? That was actually us. Here is a hybrid, or excuse me, a patent on our first passive harmonic filter. And since then, there's been a lot of development. There are a lot of people building these. This is the #1 harmonic mitigation method for variable frequency drives. And the reason for that is you got a very high performance to cost ratio. You have excellent performance on the order of some of the much more expensive technologies, but these are very inexpensive. I want to mention one other thing. Look at this. You have got you've got a reactor here. You got another reactor here, and then you have a 5th harmonic filter shunt tuned. Guess what? This is basically a low pass filter. And this is an excellent low pass filter. So in addition to getting harmonic control, you also get excellent surge protection. That is a big advantage of a passive filter. This is a passive filter in a somewhat oversized cabinet. So you can see we have 1, 2, 3 reactors and 1 or more capacitors. And all those capacitors are doing a very different thing than the capacitors on the DC bus. But we can, and lots of people can, go ahead and package that entire filter with the drive. So it's all UL tested and rated in the shop. You just install the 1 box and you're good to go. You can also buy harmonic filters that go on after that. Now let's get into the active bridge. So most of the rest of today, we're going to be talking about active technology. Active technology is kind of like the cat's meow. So here's our active technology. It looks just like a standard drive, except that instead of diodes on the front end, we have IGBTs, and those IGBTs turn on and off in order to create sine wave current going into the drive. They do an excellent job of that and can get down to total harmonic distortion levels of 2 to 5%. Very, very low. If you look at these at full load, even on a system with high voltage unbalance, we see on a very high quality drive on the order of 2.5% total harmonic current distortion. That's really nice. However, because these are turning on and off and they're eliminating the lower harmonics, they're great, but every time they turn on and off, they create switching noise. And that switching noise we have to worry about on our distribution system. So we solved one problem, we created another. And so we have to add this LCL circuit. And the LCL circuit, what does it look like? It looks like a low pass filter. But in this case, it's smaller because all we're trying to do is get rid of that very high frequency switching noise. And one of the figures of merit for a really good active front end drive is the quality of that filter. Now here's a picture of a job that we did. And in this case, we had a standard variable frequency drive. We put an active front end on that drive. So we're using the active front end as the converter, and then we went right into the existing DC bus on the standard drive. Notice that our filter, we've got the reactors in the bottom, and then we've got that input circuit in the middle that has your capacitor. And so, sorry, that is the filter that filters out the high frequency switching noise from the active filter. This did an excellent job, and we were seeing around 2.5% distortion, which I will show you in a moment. Now we're going to talk about a different active technology. That's called an active filter. So that there's no confusing, we're going to refer to this as an active bridge and this as an active filter. So an active bridge is a device that is either added to a variable frequency drive or part of that variable frequency drive, whereas an active filter is on the bus as a separate item. So in this case, we have our VFDs, we go ahead and let them produce harmonics, and then we put in an active filter in order to mitigate those harmonics or filter those harmonics. Now, as I said, if we're going to get our maximum performance, we'd really prefer those variable frequency drives to have line reactors. The more impedance we have between the active filter and the VFDs, the better job that active filter is going to do. So if you have your VFDs down in the plant somewhere, or VFDs spread throughout the plant, and put the active filter up near the service entrance, that also works pretty well. But we're a big fan of AC line reactors for reasons that I think I've already covered. Now, our total harmonic current distortion is variable because it's programmable, and it depends upon how much correction you're putting in there as an active filter. The maximum attenuation ratio, rule of thumb, is 10:1. So what that means is if you have 100% harmonics, you're probably not going to get down to better than 10% harmonics. That's a 10:1 ratio. But that's unusual. If you have 30% harmonics, say on your drives, you probably can get down to around 3% harmonic distortion. Now, how do they work? Well, the best example that I can think of has to do with noise canceling headphones. I would call this a metaphor, but it isn't really a metaphor. It's exactly how harmonic filters work. And the only difference is noise canceling headphones do it with acoustic waves, and harmonic filters do it with voltages and currents, primarily currents. So a lot of you have had experience with this. Some of these you can actually turn the noise cancellation on and off. If you get on a plane, you put this over your ears, you could still hear that plane rumble, and then you switch on the noise cancellation, and it's phenomenal. I mean, it's miraculous. All of a sudden, it's just completely quiet. So the way they work is they have a microphone, and the microphone measures the noise coming through those headphones, and then we have a speaker, and the speaker creates more noise. But the more noise that it creates is 180 degrees out of phase with the noise coming in through the ear cups and from the plane. So because it's 180 degrees out of phase, it cancels the noise coming in from the plane. That's exactly the way that active filters work. Not active bridges in the drive, but active filters on the bus. So up on top, you can see on the left before, there's our harmonic spectrum. We've colored the fundamental green, and that's the good harmonic, and then all the reds are the bad ones. In number 2, we use the active filter to create noise that will cancel those harmonics by making the currents 180 degrees out of phase with the harmonics. And the result is we get rid of the harmonics, and we're simply left with that first harmonic, which is our sine wave. In row 2, we have a typical waveform. In column 1, On column 2, you can see a rather odd waveform generated by the harmonic filter, but that will cancel the harmonics in column 1, and we end up with a nice sine wave. Now, we are going to talk about power factor correction in a minute, but I just want to mention here that the active harmonic filters, in addition to being able to do harmonic mitigation, can also correct your power factor, and they can also correct voltage imbalance if that is something you need. So I've divided all these things up in level 0 to level 4. Level 0 says we got nothing, and then as we get better and better technologies, you can see that our performance gets better and better. Let's look at IEEE 519. This is a utility standard, and the utility standard says that we will allow you to have, over here on the right, in the total dynamic distortion, that's your total harmonic current distortion. If you have a very strong or a very weak utility and a big load, they will only let you have 5% distortion. On the other hand, if we go down to the bottom of that TDD row, if you have a very strong system and a very small load, then you can have 20% distortion. So as all the engineers will know, this is kind of a pain because you've got to go to the utility and find out what the short circuit current is before you can do these calculations. What we find is that in almost all cases, you're going to be in the 12 or 15% category. So many people think of 5% as IEEE 519. That's not really true. It's extremely unusual that you have to get down to 5%. And even on very, very big systems, and I do these calculations all the time, I generally come up with a 12 or 15% category. So we have to get to there. Now, if you are out of compliance with the standard, they can cut your power off, they can fine you, and so it is an important standard. The point of common coupling is where they measure that. This is from the IEEE 519 working group. It says they measure that at the closest point on the utility side of the customer's service where another utility customer is or could be supplied. So an example here, we'll show you our transformer that's dedicated, and if there are no customers connected on the load side of that transformer, then our PCC is going to be on the line side of that transformer, and that helps us quite a bit because our short circuit currents tend to be higher up there, and therefore we'll get a more lenient situation on the harmonic correction. These is a price comparison. Right down here is our line reactors. They only add about 5% to the assembled cost of a drive, and as you know, I love line reactors. The highest one up here is actually 18 pulse. You could get 12, 18, 24 pulse drives. They work well, generally give you about 7 to 8% harmonic distortion, but they tend to be very pricey. This is your active harmonic filter in red, and your active front end or your active bridge in green. So you can see it's significantly more expensive than this dashed line down here, and my cursor right there, that's your passive filter. So that explains why the passive filters are so popular. They give you 7 to 8% harmonic distortion typically, and they'll only add about 30 to 40% to the price, as opposed to an active front end that will double the price. So in general, this is the most cost-effective way of going. However, let's say you have a number of smaller drives, and you would have to put a passive filter on every one of those drives. It actually is less expensive in systems with lots of small drives to go ahead and use an active filter rather than to put a passive filter on each one of the drives. It will give you actually better harmonics because the active filter can get clear down there way below 5%. And it becomes cheaper when you consider that you're only using one active filter, and on the drives you would have to use a harmonic filter on every single drive. So prices are all over the place, as you can see, but that gives you kind of a feel for our costs on some of those. How about voltage distortion? Well, voltage distortion is also recommended by the IEEE 519, but not enforced. The only thing they enforce is the current distortion going back into their system. The voltage distortion on your system is your responsibility, but they recommend 8%. So our recommendation is generally under 12% harmonics is good. I want to point down here, transformers should not be loaded more than 50% with VFDs. Why? Because your voltage distortion can get too high. Generators should not be loaded more than 50% with VFDs. Why? Because your voltage distortion can get too high. So if you're using an active filter, let's say, that active filter does a great job for the utility and is an excellent technology, but you still could end up with higher voltage distortions than you want down within your facility. If you correct your VFDs to have less than 15% harmonic current, then we don't worry, we can load the transformers or generators all the way up. Here's some filter complications. That's a 12 pulse. You can see that 12 pulse at lower loads and higher voltage imbalance causes those to have appreciably it causes, they don't perform as well if you have voltage imbalance or at lower loads. Here's an 18 pulse, same thing. It is affected by voltage imbalance because it starts out down here around 4 or 5%. Then even with lower loads and some appreciable voltage imbalance, you generally do pretty well. 18 pulse typically performs about the same as a passive filter, around 7 or 8% in real systems. This is a hybrid filter. This is one I measured on one of our filters. And as you can see, we were measuring 6.9%, but it's very well behaved. And when you get into lower loads, it actually does better. This is the one we want to look at. There's an active bridge. So this is the one inside the VFD. And you can see I've used, it doesn't look as good because I only went from 0 to 20% over here. But notice here at 100%, we're about 2.5% distortion. That is incredible. And this was on a system in our shop, which because of the utility feed has high voltage imbalance. So active bridge can handle voltage imbalance very well. If you go down to very low values, it doesn't perform as well. But also when you get to low loads like this, even though the percentage is high, probably doesn't matter because the currents are still low because they're a percentage of a very small value. So this is excellent performance. Here's an active filter. The active filter, we just shaded it in. You can get generally down to 3% on an active filter, but maybe you don't need 3%. Maybe 15% is good enough for you, or we shaded this up to 20% because that's the highest level in IEEE 519, and depends on the size of the filter. You could do anywhere in there, but it's pretty easy. Most people who have harmonic filters want to get down around the 3, 4, 5% area. Medium voltage drives use series bridges, and here's a drive that has 2% total harmonic current distortion. Medium voltage drives are fantastic in this way. Most really good quality medium voltage drives will have excellent harmonic performance and do not need correction. Uninterruptible power supplies, you can see what's there. And again, interruptible power supplies, many of them have active front ends that you don't pay any extra for, so they tend to be a good load. We're going to talk about power factor and finish up by looking at how these things are wired in. A lot of you have seen this before. This is the beer analogy. You get a beer, and this is your apparent beer. This is the real beer, and this is the foam. It's similar on an industrial system for power factor. You have kVA, you have watts, and you have kVARs. And the kVARs are basically wasted, so we'd really like to get rid of them. This is a transformer. You can see at 80% power factor, we have 75 kVAR. If we put in capacitors, correct that to 25 kVAR, we get to 97% power factor. And you can see that the kVA, which is equivalent to the current, goes from 125 kVA down to 123, or that could be 125 amps down to 123. This is a traditional way of putting in harmonic correction. Uses stepped capacitors, and you step those capacitors on with contactors. We have lots of problems here with the capacitors failing due to harmonics. So a better way of doing that would be to use the same situation, but add reactors, typically tuned to the 4.7th harmonic. And when you add those reactors, then it helps with the harmonics and prevents any resonances. But by the time you add the reactors, you are getting to a cost point where you can almost afford an active static bar generator. So we tend to move ahead of this old technology with contactors going in and out and tuned filters to actually an active technology that acts very quickly. Let me, well, I pointed out this, generators can't withstand leading VARs very often. We can actually generate lagging bars if we want on a static bar generator. So how do they hook into the system? Well, first of all, you have to measure the current. So I'm sorry, you have to have a CT, and that CT mostly is down here measuring whatever load you're trying to correct. It could also be up here. This would be a load side CT, or we could use a line side CT. And then you have your active harmonic filter. Your active harmonic filter is a noise generator, and that noise generator generates noise. So let's say that we have a variable frequency drive with 30% harmonics. We will get 30% harmonics on this load, and then we will generate those harmonics out of the active harmonic filter. And at 0.3, then we will see the cancellation. So anything above 0.3, you will have almost a perfect sine wave. This is a picture. This was one of the first ones that we did. And so the gray one is an active harmonic filter. The white one is a static bar generator. Now I told you active harmonic filters can generate bars, but they can also do active correction. If you buy just the static bar generator, it looks the same, that's the one in white, but it will not correct for harmonics. It will only correct for bars. So why would you buy it? Because it's about half the price of the one that does the active harmonic. So we put both of them on here. This is one of our installations so that we could see how they were both operating. And this is, we're getting pretty close to the end here, a couple more minutes. Active filters restore power system to peak operating efficiency. They do harmonic correction, they do power factor correction, they achieve IEEE 519, and they have a 5-millisecond response time. So they're very fast and can respond to rapidly changing loads, like if you have welders on the system. A active harmonic filter also does a static bar, but if you just want the static bar, you can buy just that at about half the price of the full active harmonic filter. If you have larger units, and we're talking here low voltage, we can also do medium voltage at very high levels, but we can put in a rack and put in as many modules as you'd like to get higher current ratings. This is the specifications for the SVG and the AHF, and we'll be sending you a brochure that has all that in it. These are the key benefits of active harmonic filters: highest performance and flexibility. They can eliminate resonance issues. We always have resonance concerns with capacitors, and with switch capacitors, you have multiple points where that can occur. This SVG, or active harmonic filters, actually test the system and look for resonances and avoid those resonances. And if you'd like them only to generate certain harmonics, if you say, oh, I only have a fifth harmonic problem, you can only generate fifth harmonic. You just program it. They can be very cost effective when mitigating harmonics for multiple VFD systems. And you can use the leftover capacity, whatever you're not using on harmonic correction. If there's still capacity current left in the active harmonic filter, you can use that to correct power factor and or voltage imbalance. And you can program how much of that capacity, if you want, goes to harmonics, power factor, and voltage imbalance. Where are these in operation? We have lots of these in operation. The reliability has been fantastic, and they work very, very well. You have to make sure and set them up right with the right CT connections, but once they're in place, these are very, very sweet. So that's all. We will, well, I'll turn the time back to Tyler.
Absolutely. Thank you, Craig. So obviously we went through a lot. Go ahead and submit any questions you have. At this point, the webinar is finished, but we will stay on to answer any questions. However, a few notes. First, we will be following up with some information, like he mentioned, different documentation and brochures. When you registered, you should have had to give your email. We can follow up with those emails. If you want more depth or information that we are not able to provide today because of the restraints of a webinar, we can follow up also with you, with whoever invited you to this, or you can always email sales@emcsolutions.com and we can get in touch with you to provide more information. Go ahead, like I said, and submit any questions. We'll wait just a minute or two to see if any come in that Craig can answer. Otherwise, thank you for attending.
We have our first question. It says, do you have a specification that you can send us? It says Word form, and the answer is yes, we do. We can give that to you in PDF or Word, and Tyler will be sending that out to each one of you. We'll have your email address. He'll go ahead and send that to you. Tyler, did you hear that?
I did, absolutely.
Okay, good. Wanted to make sure that went out. Can we get a copy of the presentation? I'll just clear that with Paul, but I don't think that will be a problem. So yeah, I don't think that should be an issue. And maybe Tyler, you can take care of that.
Absolutely.
Yeah, we can, what we'll be doing is we've recorded this webinar and have no problem getting it out to anybody that wants the recording of the webinar.
I have another question from Chris that says, when should we be using EMC filters with VFDs? Oh, what a great question. This is where we a lot of times get into head scratching. So let me tell you my simple answer to this. In general, we're trying to hit 12%. Now, we see a lot of specs that want 5% current distortion, and of course that's great, but it is extremely difficult to get into. If you want a drive to generate 5%, the only technology that you have available is the active front end. And people who make passive filters, people who make the matrix inverters, which we haven't talked about, 12 pulse, 18 pulse, all of these people would generally try to tell you that you can get to 5%. But if you try to actually get there and go out and measure it in the field, you'll find out you don't get there. And none of them are willing to guarantee that. They're only willing to put that in their brochures. So in general, I personally try to get to 12% because that's what you need. My rule of thumb, if you have less than 25% of your total load is drives, I think all you need is line reactors. They're cheap. They do a good job at transient protection. And so if less than 25% of my total load is VFDs, I just put in reactors. That's all you really need. If more than 25% of your load is drives, then my advice is put generally the passive harmonic filter on your larger drives. If you only have a few drives, that's all that's necessary. If you have a system with lots of small drives, then I would recommend looking at the active harmonic filter, put line reactors on all the drives, and at the motor control center or the service entrance, or whether it's wherever it's convenient for you, go ahead and put an active filter there. And that actually will get you down below 5% harmonic distortion. But make sure that you're not going to have high voltage distortion somewhere in the facility, because that active harmonic filter is only correcting it at the point where it's tied into the system. This says, what would you recommend for a system with multiple 150 horsepower to 500 horsepower drives? That's a very interesting question, because we have multiple drives, and so that makes me think, oh, we should use a active filter. But as you can see, the drives are very large, and because they're large, that active filter is going to be large, and it's going to be expensive. So the active filter would work pretty well, but because the drives are large, I'm going to have harmonic currents in my system. And in general, I would recommend on a system like that using probably the passive filters in most cases. And not using the active filter. But every situation is different. We have to look at it, see what the power distribution system looks like. But generally, you're going to get your best performance at your lowest cost in the larger drives by using a passive filter. If you want to use one of the other technologies, perfectly fine, but it's going to drive the cost up. By the way, let me mention one other thing. On the active filter, sometimes if the drive is off, there's a capacitor there, it generates leading bars, and sometimes people are concerned about having too many leading bars on the system. This is generally pretty easy to correct by simply specifying a capacitor cutout contactor on your passive filter. And what that does is keep the capacitor in the filter off when the drive is off. And when the drive starts, if it's at very low frequencies where you have very little current, then we still keep that capacitor off. When we get up to maybe 30% speed or 40% speed, then we go ahead and turn that capacitor on, and that brings in the full harmonic correction. And that way, it almost always corrects any problems that you might have with leading power factor. And leading power factor can affect standby generators.
Craig, we had Luke actually bring up as one of the questions, wanted to make sure that we answered Chris's question on the EMC filter. Didn't know if he was referring to EMC filters or that come internal to some VFDs.
Well, I don't know. When I say filter, when you said the filter, I assume that's the 3 reactors on the capacitor passive filters. And so that was my intention to answer it in that way. And that's where I'm saying those filters generally get you down to 7 or 8% distortion. And so I would use that passive filter, which is going to add 30–35% to the cost of a variable frequency drive. I would add that in there whenever my VFDs are more than 25% of the total load, or go with the active. If it's lots of small motors, then we're better off going with an active filter. So when I answered that, that was what I thought was meant. Now, EMC, TCI, MTE, Miras, all these people make filters that are pretty similar. The nice thing about the EMC filters for me is that we generally package them with the drive. So instead of getting 2 boxes that you have to mount and wire between and then hope you get everything wired right, at EMC, we generally like to put that filter in the drive cabinet with the drive and test it all at the factory before it leaves the factory. So you've only got one enclosure.
Okay, we had a couple other questions come in. Jim asked if we have a chart that shows the size line reactors to use for each size drive.
We do have that, and I could have, maybe Tyler, could you send that out? Obviously, the chart means we're going to have to send that to them, but definitely, and in general, if you know the voltage and you know the horsepower, then there will be a chart that shows the size of the line reactor. As I mentioned, there are different impedance line reactors. So typically we have a standard impedance, which is a 3% line reactor, and a high impedance, which is a 5% line reactor. The 5% line reactor is better, but costs a little bit more. And so most people go with the 3% just because they don't want to spend a little bit more on a 5%. But if you specify a 5%, it'll do a better job both on harmonics and on surge protection. And it doesn't cost that much more. You know, maybe the line reactor is a fairly small part of the drive. So maybe the line reactor of 5% might be 50% or 40% maybe more than a 3% line reactor. But since it's such a small part of the cost of the drive, it really doesn't mean much difference in terms of that drive. Steve Rossiter. Oh, okay. So now the Steve Rossiter has asked a question. He's in reference to Chris. He's saying, are we talking about the harmonic filters, or could this refer to an EMI RFI filter? Of course, the EMI RFI filter is available. It doesn't have anything to do with harmonics, so we haven't really addressed it today, but this is a way of mitigating airborne noise. And so that is another option that's available if you're having airborne noise on your causing static on your radios and things like that. Then your electromagnetic interference, radio frequency interference, there are separate filters that accomplish that. And those filters do not do anything for harmonics. The harmonic filters don't do a lot for EMI, RFI. It's a different issue.
Great, thank you. If we didn't completely answer your question, or you have more questions that you think we could follow up on, like I said, feel free to reach out to us at sales@emcsolutions.com, reach out to the person who gave you the invitation for this webinar, or respond to the email we send out with other information and documents. Otherwise, thank you so much for attending today, and we look forward to talking to you in the future.